Hello, welcome to another episode of Rustacean Station. I'm your host, Alan Wyma. Before we start, I'm excited to share that we're hosting Rust Asia Conference 2025 on March 28th in Hong Kong. This is your chance to dive into the world of Rust in Asia and beyond. We've already got Tim McNamara, the author of Rust in Action, as our keynote speaker, and more speakers will be announced soon. We're still open to speaker proposals until December 31st, so get yours in now. Don't miss out. Our early bird ticket deals wrap up by Thanksgiving, November 28th. Check out all the details at www.rustasiaconf.com. Now back to the episode. Today we have a very special guest. It's Andrew Lam, who's a staff engineer over at InfluxData. Andrew, why don't you go ahead and introduce yourself?
Yeah, so my name is Andrew Lam. I'm a staff engineer at InfluxData right now. I've been working in sort of system software programming for over 20 years now, which is somewhat terrifying. I like to joke that my experience can almost drink now. So what I've been doing the last 4 years is I've been working on the new version of InfluxDB, which is InfluxDB 3.0. But prior to that, I spent several years I worked at Oracle for a while, writing in C on the server code. I then worked on embedded compilers in a network device, which is also written in C++. I worked at a company called Vertica, which is a distributed database for 6 years, also written in C++. And then I spent about 8 years working at various machine learning startups doing various things as one does. And now I've spent the last 4 years really focused on database implementation of InfluxDB 3.0, which has all been Rust. So that's been a phenomenal experience. And I'm a huge Rust believer now, especially after having done it for many, many years professionally in C++.
Did I hear correctly that this is your first time working with Rust once you got over to Influx? Is that right?
That's right. That's right. And I give Paul Dix, the co-founder of InfluxDB, all the credit in the world. So at the point of my career when I was looking to do, this is 4 years ago, I had been basically being management in a variety of startups, and I was just ready to get back to more of the technical aspects, especially databases, which is something I'd really enjoyed previously in my career. And through various connections, I got hooked up with Paul, and Paul's like, we're going to write a new database. It's going to be in Rust. I need a new storage engine. We're going to use these technologies, which I'd never heard of, called Apache Arrow and DataFusion and Flight, and like, it's going to be great. At that point, I thought Rust was kind of a hipster language, which I can talk more about that. I was a big C++ guy, but it was just ready enough for a change that I took the plunge, and Paul, was great and let me focus on learning it. And I've become a huge believer since then. So yeah, I've never programmed in Rust professionally before this job, although now I've been doing it for 4 years. So I'm not sure I really qualify as a beginner anymore either.
Well, this is something I would love to hear about because I did try to introduce Rust to some more experienced C++ programmers, and they kind of just blew it off and said, oh, we have, I forgot what it's called. This is RAII, like the automatic reference counted pointers of some sort. They kept saying we have this, we have that. Or, you always get the argument, oh, I'm just a very good programmer. Those guys just don't know what they're doing. Obviously I know what I'm doing. Do you mind to kind of shed some more light on what your experience was as walking into this whole, like you said, it's a hipster language, which I think is the first time I've heard that about Rust.
I would say my perspective on Rust was not dissimilar to what you just described when I was first coming in. My context had been before, basically I was an architect for a large machine learning platform. And so that major challenge there was integrating lots of different technologies and technology stacks. And so we had Python, we had C, we had, we had all this stuff. And so a bunch of the new young developers were like, hey, we found this new language. We need, it's Rust. It's great. It's going to be awesome. And at that particular company, like the last thing that the company needed was like yet another technology in its stack, right? So like I had already these guys are just trying to basically find an excuse to add something else to an already complicated stack. That was like my first experience to hearing people talk about it, right? You see all these ampersands, like what the hell are you talking about? That's partly where this hipster thing came from, right? It was like all the young kids are like excited about something that they read on Hacker News, rather than like, hey, we got a job to actually do, and ship real code. Then fast forward to when I joined Influx, I was like, all right, it's the pandemic. I need the code. Rust is fine, whatever. And the first 3 months of Rust was very painful because there were a bunch of things I'd done as a C++ programmer that like the Rust compiler just wouldn't let you do. It's very confusing. And there were these terms that were not familiar, like, interior mutability, right? Like basically when you need to lock it, right? Like you need a mutex. That's what that means. But like that term was very confusing. And so figuring out the common patterns, it was super frustrating for the first 3 months, right? And I was like, maybe we should just write this whole thing as C++. But like I said, my perspective has changed a bunch. And I'll tell you some anecdotes about why. For example, one of the past things I worked on in C++ was it was a desktop app, whatever. It basically had an asynchronous run network loop in it. and it had a bunch of, which has a bunch of callbacks. It was written in Boost, used the Boost ASIO framework. And it turned out actually when you shut the app, it would actually segfault, right? Like it would just crash. No one really paid attention because you were shutting the app down anyway, so no one really cared. But then when we were converting it to server, like it mattered a lot that it was segfaulting. So I spent a whole bunch of time chasing down, and it was basically like use after free pointers because there were like references hanging around in the callbacks that basically got used as part of the shutdown of the thread handler. So I saw that as an example because I spent a whole bunch of time and eventually fixed it with using this thing called STD, a shared pointer rather, which is the equivalent of like a Rust arc. In the course of my 4 years at Influx, working at Rust in databases, right, all the same sort of low-level stuff, you maybe could argue I've tracked one memory crash down, maybe, but like it was really an overflow and some offset accounting thing. Versus my past life in C++ programs, I spent a huge amount of my time chasing down weird crashes that eventually turned out to be pointer corruption problems, either because I wrote it, right, I wrote some bug, or often because someone else wrote a bug, right, that has a use after free, which is super insidious because they're often fine, except under load after 3 days of beating on it or whatever. So originally the pitch from my perspective of Rust was like, once you satisfy the compiler, you don't have to spend any time chasing down runtime crashes, right, or race conditions, which sounds almost too good to be true, except that's been basically exactly my experience actually doing it. So like once it compiles, it basically just runs and it's fast. So that's like my perspective. It's been very, very good.
I'm kind of curious about like that aha moment when you finally like it started clicking and you're like, okay, because I think most people have this initial time where they're fighting the borrow checker or another piece possibly. Usually it's the borrow checker. And finally things start kind of clicking and you're like, oh, this is actually really nice and this kind of saved me. Or do you remember that kind of moment?
I'm not sure for me it was ever a single moment that like, oh, this is a great experience. At some point it was like I stopped having to fight it because I just understood the pattern that it expected. So you just then follow the pattern, you stop having to fight the thing. What dawned on me is, right, you look back 2 or 3 years in, right, running production distributed systems in Influx and InfluxDB 3.0, we brought it to market. We're running, it's not just you're running some web app, right? Like it's doing large scale distributed data processing. And like I hadn't had to chase down a crash, right? Or some weird multi-threaded race condition, or some of these other things, which actually consumed a huge amount of my time earlier on in my career. Because like you get one of these things and you spend like a week, no joke, trying to figure it out because it would only happen under very hard to reproduce circumstances, if ever. And so you'd have to do like this huge amount of code, exploration and mental gaming to try to figure out what was going on. And I looked back at some point, like, I haven't had to do any of that here. And that's because of Rust.
What about when you have to write out the lifetimes for function calls and things like that, or even structs? How's that been? It's kind of a whole new thing, right?
Yeah, the lifetimes is somewhat of a pain, like, but it's no, in my opinion, all that much worse than doing the C++ templating stuff, right? Like that has its own magic, and it's a little hard on the eyes to see all those apostrophes and whatnot. But basically, a couple of times the borrow checkers maybe gotten it wrong as some sort of complicated async function, right? Like you can't really understand what it's talking about. It can't blah, 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 blah. I often will, I don't know if you've experienced that or your listeners have experienced that. I have learned to just basically love arcs and stop worrying about the potential runtime overhead of that compared to like just getting a thing to compile. So like my suggestion to users, if you're getting bogged down in some crazy borrow checker problem in async code specifically, arcs are fine, right? Like yes, they might have some tiny amount of overhead, but compared to all the other stuff you're doing, it's probably okay. And then you can always optimize it later. I read some blog post somewhere that I think got it right. I think it was from the Spice AI guys, or maybe the LDF guys. They basically said when you're starting to write your Rust program, at first basically just write it using clone with reckless abandon, right? Like I know this sounds terrible, and you don't actually want to clone everything. But if you're in trouble with the borrow checker, just clone, right? Like that's the way to get around a lot of those problems. And then when you want to go back and sort of optimize for performance, then spend your time sort of carefully working out the lifetimes or whatever. And I think that often is more effective. Like you end up being a more productive programmer because you end up generating more useful code, even though some of it might not be as optimal as possible. You might do a couple clones. If you worry about like minimizing all clones all the time, that's probably premature optimization.
I've heard that so many times. Something that kind of came to my mind is if you've been doing C, C++ for so long, you probably are used to like a set of tools that can help you to find things. Like Valgrind, I think, is one I've heard a couple of times.
Oh, yeah. Oh, I use Valgrind many, many times.
Well, how about the tooling situation in Rust? Because it's still quite, young compared to C, C++. Have you ever found that you're missing a tool that you needed, or has it just been that things just kind of work and you're like, I don't need Valgrind or anything else? I think Valgrind's is for spotting like memory issues or something, right?
Yeah, I mean, basically all the tools exist. That's the short answer. And the longer answer is part of that's because both Rust and now modern C++ are built on top of like the LLVM stack. And so there's like a real debugger, right? And a real linker and a real, you have all the basic like low-level tools you need. Like you can it does memory allocators and heap profilers and all that sort of stuff. Because it's native code and it's all sort of using the same underlying infrastructure, it's all pretty mature, I've found. So like, for example, I work on the development machine is Mac, like most people. That's also a hipster thing. That's another story. But, you can use the native Mac X tools, like Xcode instruments tool to do profiling. And it works great because Rust just native code. You look at it, you look at a little stack trace and stuff. So I've been quite happy with the tooling I've found.
Is there any tools that you think are missing, or you're pretty happy with everything and it's not really been a problem?
Whenever you're doing profiling, it would be nice to have like tools that could tell you exactly where all the time is being spent. But I've never found that in any language. So I mean, maybe Go is pretty good, but I've been pretty happy with the tools.
Obviously, a lot of things are happening with this new rewrite. Do you mind to kind of quickly talk about what is Influx and what brought this whole kind of big rewrite? Because rewrite is it's a pretty big endeavor, right? I mean, you're starting from scratch, basically, a whole different code base, and you're restructuring everything, I think.
So let me talk about InfluxDB and maybe time series databases in general first, and then we can talk about the InfluxDB 3.0 version. So databases obviously are responsible for storing data, right, of various types. Relational databases are probably the type of database that most people are most familiar with, and that sort of stores data in a table model. That's the classic one. I think what we've seen over the last 30 years in the industry is that rather than having fewer, more monolithic databases that do everything, instead what's actually happened is that there's many more databases that are all specialized for various different workloads. I think that was a trend that started at least 20 years ago and it's just accelerated since then. So the thing that drives that, I think, is typically you can get 10 times better performance if you spend your time focused on a particular use case rather than it's just some sort of general purpose, right? So the reason people don't just run Oracle or Postgres everywhere. There's lots of other use cases and different optimization points. So time series is one of those. And so the time series workload, in some ways, you might say, well, I could just use a relational database and like put a time column in there, right? What's the difference, right? Which you can do that. But I think what people found probably about 10 years ago was that there were a bunch of features that if you focused on, you can make the experience of using time series data in a database much, much better. So the first thing that was very common, I'm talking about this in general, but this is all basically like Influx is one of the major innovators in this space, is as data is coming in, most time series applications, especially when you do like monitoring and metrics, it's very important to get the data as quickly as you possibly can into a format that can show up in your query results. So like a classic original Influx use case was you're trying to drive monitoring, right? You're monitoring a bunch of servers or something. And so as the data comes in, you want it to like appear in your dashboard as soon as possible when it comes in. And so whereas a lot of traditional transactional databases, like they would struggle to keep up with the rate of ingest at an economical time. So basically, you can do fast ingest, very fast query, and there's a lot of query, very fast on the leading edge. And then there's also like a huge drop off in the value of data. So like the data that just came in is really, really valuable, whereas the data from like 2 weeks ago, whatever your server CPU was doing, it might have value, but it's much less than the most recent data. And so there's this like lifetime that's important to manage as well. And then finally, most relational databases require you to basically define schema up front. So maybe it's a little different these days, with JSON schemas or whatever. But time series databases are very good at like they'll just accept new data, and as new columns appear in the data, they'll be able to sort of generate those columns on the fly. So the combination of sort of those features and really focusing on them. Oh, and also querying. If you've ever tried to write time series queries in SQL, like computer moving average right over time, you'll find it's a very painful experience to try to do that in standard SQL. So the time series database category, Influx being one of the leaders, was focusing on that particular use case of getting time series in, make it queryable, make it understandable quickly, and then handle its lifecycle going through. That was the primary reason for time series databases. All of the classic time series databases, including Influx 1 and 2, are basically built on a technology called LSM trees or some variant thereof, which is a way of organizing the data so that the most recent data for a particular device or server or whatever you're measuring happens to be all close together. That type of organization is great for queries where you've got, like I just want to know something about this one server or maybe this 10 servers. But as use cases got more advanced, like I have hundreds of thousands of servers maybe, or I have lots, like I want to monitor individual Kubernetes containers. Now there's like millions of them, or I want to monitor huge numbers of networking edge devices, right, or IoT devices, and there's millions of them. The number of distinct things you're measuring, in particular which is called cardinality in the time series use case, becomes much bigger than in classic times. And I think the LSM tree based systems were struggling very much to keep up with those high cardinality use cases, Influx in particular. So I think that use case, high cardinality, coupled with the fact that Influx, and again, all of its contemporaries, are basically designed to work with locally attached disks. And as the cloud became more prevalent in data centers, there's been a huge shift in basically anything that processes data from managing locally attached storage, right, in your EBS volume or a local disk or an NVMe or something. Basically, everyone's storage is moving to object store, so S3 or GCP blob store or Azure blob store, because it's so much cheaper. It's like 10 times cheaper. And so I think those were two of the major technical drivers that drove Paul, the co-founder, to decide he needed to rewrite the architecture in version 3. And I will be totally honest that I am probably more on the engineering optimization side, where if I got told this, I'd probably sit there and try to optimize the existing system more and would probably end up in a local minima. But Paul is not like that. Paul is just like, we're going to do the right thing and do a shift and get out of the local minimum. So I guess I'm trying to say, he was the one who picked that, and he wrote a blog post maybe probably about 4 years ago, right before I joined, that said, we need to rewrite the core of the database, and here's why. But the question becomes, if you look at the history of creating databases, right, database companies, it takes tens of millions of dollars at least to do it, because you've got to hire a bunch of people for some number of years and just let them hack on it. So one of the bets that Paul made was, we don't have to rewrite the whole thing from scratch, from the ground up. Instead, we're going to rely on these, sequence of technologies that I think I mentioned before, like Apache Arrow, Apache Flights, Apache Parquet, and now Apache DataFusion. Those basically form the foundation of the types of things you need to build a modern analytic database, which are required, but they're not particularly differentiated, and it's well understood now how to build them. So like how you represent the data in memory for fast processing and vectorized execution, how you send it over the network quickly, how you store it on object store efficiently, right, Parquet, how you write a query engine that can actually process SQL queries, which is what DataFusion does. The bet was, Influx as a company had a long history of open source contribution and really believing in open source. Now, having worked there for 4 years, it's very, very much part of the DNA. And so the idea was, we can band together, use our experience in open source, help drive some of these bigger open source projects, and both benefit from the contributions, but also then give back to the overall community. So like we can all kind of build this shared foundation together, get something much better than we possibly could have built by ourselves, and then spend most of the engineering time on like the features that are really important for our use case. So like Influx has however many people working on InfluxDB 3.0, only myself and like maybe one other person really focus on DataFusion Arrow, like the low level pieces. And then most of it, Influx's time is spent on the higher level new features to support high cardinality and make time series query really nice and all the higher level things.
So you're relying on these other pieces. So are you doing upstreaming them in terms of like making that stuff better and then sending it back upstream to those projects and then?
Oh, absolutely.
Okay.
With full support and encouragement of Paul and Influx in general. Like, so I'm on the PMC of the Apache Arrow project, and I spend a significant amount of my time maintaining the upstream Arrow RS implementation of Arrow, and part of that also has the Rust implementation of Parquet and DataFusion on the PMC of that as well. So yeah, not only are we upstreaming it, we're also actively contributing to like the governance and running of the programs. And I think that was a very deliberate strategic choice on Influx's part, because they believe in open source, like really fundamentally. And I'm very biased, right, because I'm like in the middle of all this, but I think it's been a great payoff for the amount of stuff we've been able to put into InfluxDB 3.0. There's no way we would have been able to do that level of features and performance and stuff if we had to build it all from scratch ourselves. It's just too big of a project. But by working all together, upstreaming it, we help people upstream, but then they also, the stuff they contribute flows back down into our product as well.
Well, how has it been for the upstreaming? Because obviously some things you may think are important or you may think should be in there. Maybe you get some pushback saying we don't think this is in line with what we want to do, etc. How do you handle these kinds of things that happen?
Turns out my previous job prepared me very well for this, which is like I was basically helping organize 300 enterprise developers, across a bunch of different countries. So like the answer is always communication, right? And there are in fact several times when we proposed sending stuff upstream that other people upstream didn't think was necessarily fitting, specifically like stuff that's 2 time series focused. There's this gap filling feature I'm thinking of specifically. And I think what we've done is we've had the conversation rather than just showing up with a giant PR of code, right? Be like, hey, let's take it or not. Right? We had the discussion first. And then I think also something that's worked really well at DataFusion has really been to focus on the APIs, right? So maybe some particular feature doesn't belong in DataFusion, but I think we've had good luck with like making sure that there's sufficient APIs that you can extend DataFusion to basically have whatever features you need, basically extend it anywhere. And so then that becomes the mechanism of, well, if a particular feature we're working on doesn't maybe fit in there, as long as we can help improve the API so it's easier for us, right? It's easier for us to integrate our feature downstream. But also then that turns around and helps other people too to build things on top of DataFusion, which I think has worked out quite well in general.
So you probably have some glue libraries, things like that. You can also open source and people can use those kinds of things, right? Here and there.
You got to understand the philosophy of DataFusion is part of this new like wave of composable database engines where we're not the only people who observed that like the core of the database, especially core analytic databases, right, that like crunch a bunch of numbers and compute summaries on them or whatever. How to do that is actually pretty well understood now. It's not easy. It still takes a lot of work, but it's basically well understood. It's like they researched it 20 years ago. There's a bunch of seminal papers about it. And then there's been like basically 3 waves of commercialization subsequently. So like rebuilding it yet again, there's very little value in doing that. So the pitch is we can all use these shared foundations. And so DataFusion's goal is to let other people build on top of it. So there's a huge focus on making sure that the APIs are there so that if you want to add new operators or new ways of processing data or new SQL, like new query languages or something, it's all set up to do that. And that's sort of one of its main design goals. And so we typically will build directly on top of those APIs. And if we find we can't do something, we'll then go propose, extending the DataFusion APIs to let us extend it. And other people do the same thing. And I think it's worked out pretty well.
So the big question is, that comes to my mind at least, is I'm a big user of Postgres. It works well for me. I don't have a lot of time series data. But the thing that always worries me is, will my database driver I use right now, my programming language, will it actually connect to this new version? How easy can I use the next set of features? So now we're on, 2.7. I just look up the version number. Yeah, 276. So 3.0 is, I believe, the next one that you're working on. So usually, when you have a major change, it could be a major API change. Are we looking at something like this, or is there like this backwards compatibility layer and say like a version 2 or next version that supports the same features as the original one plus more? What are we looking at in terms of that kind of compatibility and that mindset?
Yeah, so in terms of InfluxDB 3.0, right, like the short answer is there's compatible APIs. But one of the things I spent a non-trivial amount of my time doing was implementing the data model that Influx exposes actually isn't directly relational. It's this thing called line protocol, right? That's the input model. But internally, we map it to a relational model so we can store in Postgres. So we spent a lot of time making it so that you basically add data the same way, right? You can use Telegraph. Data comes in the same, the exact same endpoints. Telegraph doesn't even know the difference. And then another thing we've done that's cool is we've actually implemented InfluxQL, which is the query language from Influx 2, where Influx 1 and 2 had a special, it's called InfluxQL. It's kind of like SQL, but it's its own domain-specific language. It's much nicer to do certain time series queries than SQL. So we actually have implemented InfluxQL, again, on top of like Parquet and in 3.0. Part of how we did that, by the way, is because we just wrote the InfluxQL front end and we didn't have to write all the sort of implementation pieces that actually run the query. We still use DataFusion for that, but we have our own front end. So the vision is you can basically use all the same V2 APIs with V3. There's a few that aren't yet implemented, but we're getting there. I think it's been a real challenge, and you've seen it with many companies, of like, how do you commercialize a successful open source product? I think Paul Dix has been sort of on the forefront of trying to various different ways. Because like you said, right, you've used Influx a lot. My suspicion is you probably never paid the company any money. Not trying to put you on the spot, but people are reassessing how to best sort of build businesses around open source, how to contribute back, but also how to actually get paid and not have someone like, one of the big cloud providers come and host your software and take all your money without having to invest the time in the development.
Yeah, I was just taking a look at the source code of the version 2 and taking a look, and I see all these .go files.
Absolutely. It's all written in Go.
This is not the first database I've ever heard of that's originally written in Go and now going to Rust. I'm kind of curious about why people ever thought that writing a database in Go was a good idea, because to me, it's a GC language, right? So I'm just thinking as a database, you need to worry about like if you get caught in, one of those GC stages and you're trying to save data, and that comes to my mind, right? That's why I could never understand why somebody would want to write that in Go. Do you know why it was first written in Go?
I'm probably not the right person to talk about that. I mean, in some ways, Go was the hipster language 10 years ago, right? And like now the question is Rust going to have more staying power, especially for the lower level system stuff than Go did? Like I personally believe it will, partly because it has lower level control over memory than something like Go. But I mean, from everything I've heard, Go is super productive. It's quite a bit faster than Java. And so it was a joy to write programs in. And so a bunch of people tried writing databases in it. In some ways, you got to actually try it, right? But like, is it a good idea? Well, you don't really know until you try, right? And so I think you'd argue that there's actually quite a few successful database companies that have their implementations in Go. So I think it'd be hard for me to argue that was a bad idea. But, if I was picking which language to write a new database in, I'd probably pick Rust. Now, of course, I'm obviously super biased, but I feel like that might be the trend. I think that's a broader trend than just me. And I think part of it's just Rust. It has all the pieces, right? It's still super productive. It's fast. And you have this fun nonsense where like, you can basically embed it everywhere because it doesn't have the VM you have to deal with or memory manager. And at the end of the day, you can make it do just as terrible thing that you can make C++ do. It's just, you got to advertise it a bit more with the unsafe blocks.
The story I like about Go, at least, is it's got a lot in its standard library compared to Rust. All the things, it's got JSON and other stuff. The other thing I like too is that it's easy to cross-compile for other platforms. It's just a single binder that shoots out. You can say go, I forgot what the heck the command was, go build Mac, go build Linux, go build Windows on a single machine, which is pretty nice.
I think you can do some of that in Rust,
I tried it with Windows on my Mac and it just wasn't working. I don't know. I gave up. I dust off my Windows machine and just do it on there. It's just so much easier.
Yeah. I'm not surprised.
We said, all these great things about Rust, though, and people always compare Rust and Go and which one's better. I think you're never going to have a clear answer that's completely objective. You're going to have people, who are one way or another. But what I'm kind of curious, too, is I always like to kind of hear, like, the not so good side. We've been kind of fluffing up Rust, saying Rust is so great, works great, blah, blah, blah. There must be some things that maybe have been a bit disappointing or have not been as easier as you'd hope or that you wish were in there. Do you know of anything that's come up in this development time? Must be a couple of things now.
I can list my complaints, right? The first is it takes a while to compile / when you build stuff, Rust leaves around like gigabytes of crap in the target file. Like it should just be able to clean that stuff up rather than you have to like every now and again go delete 100 gigabytes of object files out of there. So that's one thing that's annoying, but it's certainly, I can put up with that. One of the things that Rust is really good at is if you want to add some library from crates.io, right? It's like a one-line thing in your config file and now you're done. Now the problem is what happens is that you end up with a giant dependency tree basically without even trying, right? It's because it's so easy to add stuff. I don't know how many direct dependencies InfluxDB 3.0 has, but it's hundreds and hundreds. And likewise, DataFusion is it's hundreds. And so I feel like while Rust language itself doesn't have a bunch of stuff built into the standard library, it effectively ends up with a couple of crates that are basically part of the standard library for all intents and purposes, because you basically need them to write any application, like serde JSON, for example, or Tokio to do anything with network. You basically have no choice if you want to work with the rest of the ecosystem. The governance is wildly different across the different crates, right? So like Prost is a good example of the gRPC framework. So in some ways it's good because, you have this wild, bizarre style where you can kind of pick and choose the best pieces of technology. But especially for the lower level crates, I don't think you really have a choice because they end up being depended on by higher level things. So if you pick your favorite language, you probably end up bringing serde JSON along with it because that's what they chose to do. So I worry a little bit about that, especially because some of those projects are not particularly well staffed or maintained or funded or whatever. Right? It's just some group of people hacking on it, maybe one or two people.
That's a really fantastic point to make. I feel like it's back in JavaScript where it's like your node module file is huge because it's like dependency hell, because this one depends on that and depends on that and depends on that. Yeah, it's quite painful, I can imagine.
It seems that that's the direction that modern software development is headed, for better or for worse, right? There's certainly downsides, but the upside is just how much cheaper to build software. And so I think it's going to continue down that trend. Like Python has the same exact thing, right? You have this giant dependency tree, especially you do something machine learning in Python. You go look at what actually gets pulled in. It's crazy. JavaScript, obviously, right? Like people complain about it, but it's very, very popular. And Rust, I think, followed the same model. has the same ecosystem distribution story, but then applications end up being built on top of it because or end up with this giant dependency tree, right? Like potentially a giant attack surface. Although Rust tries to be pretty good.
Yeah, I'm sure there's going to be something that's going to happen at some point, knock on wood. But somebody did try to stick something in there half a year ago or something, and luckily it's caught pretty quickly. There's another DB company I'm aware of called SerialDB. I talked to quite a few of their engineers already. They basically do everything in Rust, and that's actually helped them to easily create client libraries in other languages. Is Influx doing the same thing?
Influx's story for client library is actually even better. I think it's better than Rust. It's leveraging this Apache Arrow ecosystem we've talked about, right? And so Apache Arrow is this in-memory representation of data, which doesn't sound obviously related to clients. But what it gives you then is there's like 7 or 8 native implementations of Arrow and a whole bunch of bindings. So basically any language you're interested in has Arrow support, like with a native library. And then there's also transport across the network for data in the Arrow format, which is called Arrow Flight. And so what that practically means for Influx is the InfluxDB 3.0 client is basically a very, very thin wrapper. It's like 100 lines of code. I'm talking for the Rust one and for the Python one and the whatever. And under the covers, what it does is it just formats the request as an Arrow Flight SQL message. It gets sent to the server. It's all standard, and what comes back. The point is, rather than have to rebuild our own, like one of the things that makes a database is expensive is you got to build your own new client libraries, right, for all the different languages. The fact that we can just reuse the Arrow ones and Flight SQL specifically, right, that gives us access to a whole bunch of the SQL ecosystem, like through JDBC and ODBC drivers, is huge. And then also, you want to modify the data that comes back from InfluxDB 3.0. Well, it comes back as Arrow record batches, and you can do whatever you want with that. You can feed it to whatever your favorite Python programming framework is, right? Polarge, for example, takes Arrow, but so does DuckDB, so does Pandas, and then there's equivalent things for other language stacks. So I don't think we've really leveraged Rust for the cross-client. We really leveraged the Arrow ecosystem.
But is everything for 3.0, is that actually going to be in Rust, like every single piece of it, or is it going to be some things in other languages?
That's the vision.
That's the vision, okay. Because I do know that there's some stuff in C, C++. There's also some stuff I've seen in Java. I can't remember which pieces are, like Hadoop, I think, is done in Java.
Yeah, the Hadoop ecosystem was basically Java, yeah.
So everything's going to be 100% Rust going on from now.
I think it's pretty close to, like Rust has easy bindings to C libraries. So there's certain like low level Rust things, like some of the compression libraries maybe, that are just bindings onto a C implementation. But most of our stack is fully Rust. Certainly all the stuff we wrote is all pure Rust. There might be some of the, like I said, the lowest level dependencies might still be like C libraries that get linked in, but it's pretty much all Rust.
Now, what's the plan for getting like a 3.0 alpha or beta release?
Well, to be clear, we're running 3.0 in production on our multi-tenant clouds. And I think the challenge, I kind of referred to it earlier, is like, what's the right set of features that we can let people run as single node open source, right? And have the great experience there, but also, actually be able to get money to fund the company, have them pay us to be customers. And so Paul is in the process of completing that work. There's a blog post from a year or two ago that describes sort of the plan for open source single node, individual install versions. We're getting close. They've been working on that for a while, and I think hopefully we're going to have something good to announce recently. But the idea is there'll be an equivalent single node install of InfluxDB 3 that you can run that behaves very similar to the earlier version of Influx, but is based on the 3.0 code line and engine and whatever. And then there's a upgrade path to like the more distributed systems if you need a bigger scale.
Yeah, because I was just taking a look at some information and I saw 6 different versions of Influx. They're out there. At least what you call over here, you got Edge, which I think is mostly what, it's basically 100% open source one that everybody could use. You got Community, and then just InfluxDB. Do you mind to kind of walk through that real quick?
Yeah, I can walk through my understanding. I think it's still a little bit in flux because of they're still actively working on it. But the idea is, going back to what I was talking about earlier, like it's been a real challenge to build a successful, really scalable company that allows people to run the software open source for free on their own machines, right? Like, so I think part of the product line you just described is designed to help people get value out of the open source pieces they're using, but then also so that Influx can actually build a business to help sustain that. So the idea will be there'll be an open source version that people can use, then there'll be, which is Edge, I believe. And then there'll be a commercial version of the single node product, which is Pro. And then there'll be, various hosted versions of the distributed product, which is what we already have today. They'll all share the same core sort of processing engine, which is a large part of what I work on. but then the exact feature set and how they manage data and how they scale and stuff will differ between them. Hopefully that makes sense.
I'd like to kind of dig a little bit deeper into some of the nitty gritty about Rust and some of like the interesting stuff that we talked about. We were talking before the show about this. Is obviously one of the pieces that is really important to any kind of Rust program that's running asynchronously is some type of async runtime, right? And you are using Tokio, but you're using it a little bit differently, I think, than maybe not most people. But of course, some people know about this, but maybe you can talk about that.
Yeah, I'd love to talk about this. It's one of my pet discussion topics. All right, so as you mentioned, Tokio was designed for and is used very, very commonly as a network runtime, right? So it's designed for doing low latency network processing, and it's phenomenally good at that, right? There's lots of places you can read about how great it is, and I would say from my experience, it all lives up to the hype. Now, what Tokio actually has internally is it has a very good, what's called thread pool, right? So you basically give it tasks, so things to do, and then it has some number of operating system threads that actually, are connected to the CPUs, and then it's got a scheduler that figures out when to run what, and it's very sophisticated and does all sorts of great stuff. And when you're building a database, so if you're doing network stuff, Tokio is great. By network stuff, I mean responding to network requests in a timely fashion. If you're building a database system, especially one of these, analytic database systems, what they eventually end up doing is they're like a data flow graph. So the actual, like when you run a query, what it actually does is you can think about it as streams of data like flowing through different operators. So it's modeled as a graph. So the nodes are computations like filtering or aggregate, and then the edges are like data flowing between them. And to run those, you also need a thread pool, right? That it basically assigns work to actual threads to do the work. And so I purposely set this up because it sounds very similar, right? You need a thread pool to attach threads to tasks that you have to do. So you have like a thread pool and a task you need to do in both those cases. And so the question is, do you need a separate system to actually schedule the processing in your database engine? And my thesis early on, DataFusion did this, was like, we can use the same Tokio thread pool, the same Tokio software with its scheduler to run these CPU intensive jobs, even though it was designed for low latency network processing. And so I think the major thing, and I wrote a blog post about this, you can read it, like Tokio has all these great things going for it. The challenge, however, and it gets very confusing, is that when you're doing network processing, being able to process the network messages quickly, like with low latency as they come in, is very, very important to ensure that you don't end up with like long tail latencies of your requests. That almost always means is you basically need to have a separate thread pool, like a separate set of resources that are handling network IO. Then if you have the other side of the processing where you're just trying to rip through as much data as you possibly can, you want those to be really saturated all the time. So you need to actually keep the actual threads that are processing network requests from actually churning the data. You need to keep those separate if you want to be able to respond quickly to network requests. You can use the same software. That's the thing I think people miss. Like Tokio doesn't just have one unified thread pool in a process. You can actually set it up so there's multiple thread pools, and you can run the different types of tasks on the different thread pools. They're called runtimes in Tokio, but they're effectively thread pools under the covers. And so what you need to do is you need to ensure that you run the right work on the right thread pool. So you need to be careful which ones you task. But that's an approach we've done. It's how DataFusion works. It actually works great. I can't tell you how much time I have not spent debugging Tokio, right? Like Tokio just works and it does what it's supposed to, and it works on all the crazy corner cases and error cases, and it doesn't deadlock and it just basically works. So as long as you're careful to keep the work separate on the two thread pools, I can't say enough good things about Tokio. But I don't think everyone, frankly, really is a fan of that division. There's a lot of people who wonder, like, why do you use Tokio for the CPU bound work? You shouldn't use something like Rayon or some other, system which is maybe more common to do it. And I can tell you why. Why use Tokio? In addition to it being super optimized and high quality, the other thing that Tokio gives you that's not, I don't think, fully appreciated when you start off, is that because it uses the async features of the Rust language, you basically get compiler support. On all these processes, you effectively need to do cooperative multitasking, right? So you basically need to do a chunk of work on return control, and then do some more work on return control, or do some more work on return control. And you do return control so that the schedule, like the task scheduler, can have a chance to schedule something else that might have come in. So what Rust async does is it basically generates those return control for you, right? Like people call them continuations, or I can't remember what the Rust term is. But the point is the compiler automatically generates for you, like every time you do a wait, that effectively at the runtime returns control back to the scheduler. So by using stuff that's built into the Rust language, I think it accelerates the development of these like high performance runtime systems that much more, because you can use all the Rust stream abstractions, all the async tasks. And yes, it takes a little like to get your head around. But if you're going to build one of these fast asynchronous like CPU bound runtimes, you're going to have to basically have all the same concepts. But if you built it all yourself, like if you use Rayon, you have to be really careful to return control back to Rayon every time, after doing a certain amount of work. Versus if you just use the async tasks and await, your code looks linear, even though under the covers it's generating these continuations that the scheduler can see. I don't know if that was the most clear explanation, but I'm a huge fan of using Tokio because it leverages so much of the rest of the ecosystem.
Yeah, I'm just still trying to understand about how this works with the CPU bound tasks, right? I usually use a lot of Elixir or Erlang, which they use basically coroutines. The coroutine situation in Rust is, I think they're called cooperative. Is that right? I don't remember if it's cooperative or the other one. There's two different ones. There's different ways to do it. One is that the coroutine has to say, okay, I'm done. I yield back to you. And the other one is that it stops it, right? And in Rust's coroutines they have to yield back.
That's right. Tokio doesn't use coroutines per se, at least the way I think about coroutines, the way like earlier. Typically what a coroutine is you like actually have a whole program stack, right? Like the whole stack. And at some point, what you need to do is in order to return control back to the scheduler so the scheduler can decide to do something else, you need to have enough information to return back to where you are to continue processing, right? Like that's the thing you need to do. And so the way coroutines solve that problem is they literally have a whole extra stack, like a whole program stack. And when you return control, it like keeps the stack somewhere and switches to some other stack, right? So when your task gets rescheduled, it just swaps the stack pointer back and you continue where you were. That's what coroutines do. Or green threads, I think, is another name for the same basic concept.
So that part makes sense to me, but the part I didn't quite understand, like that part makes sense on a CPU bound part where you'd want to be able to stop execution, go to something else and go back to that. So that way you have an equal sharing of all these different concurrent parts of work. But like you said, you have to actually yield that yourself, manage all that yourself. That could be painful. You could make mistakes. But with await and async routine, once you call await, that's when it could be switching, right? That's the part I didn't quite understand about how can you use the await part in something that's CPU bound, because most CPU bound things that I'm aware of, they don't really have a part where they're going to say, okay, now we do something asynchronously. So you're saying that you actually have to add that to yourself.
That's right. So you have to basically do the equivalent of calling await. Inside DataFusion or this CPU bound stuff is processed as like in batches. So typically what it'll look like is you get 8,000 rows or something that you'll do work and then you'll return control after you process those batches. So there's oftentimes an obvious point to return control because, like, for example, now you need the next input, right? So you processed whatever input you had and now the task needs the next block, right? So you say, all right, I need the next block. The way that looks in the code is like, give me next block dot await, right? And so the code just looks like it got the next block and carries on, even though what actually happened was the Rust compiler generated a return. The scheduler went and did its thing, probably ran the code to generate the next, to schedule the input to generate the next block, and then return control to you. So you wrote code as though it's just linear, even though the compiler is actually returned control for you.
Do you mind to talk a little bit more in depth about what that pull function would look like? Is it just already returning ready? I mean, or is there actually a pending with
Yeah.
something happening? It just returns ready. Okay, that's kind of a way to like fake it. Yeah.
It depends on what the operators are, but you can actually look at the core processing streams in DataFusion are Rust streams. Like they implement poll and poll ready, and so depending on whether they have output ready, right, they'll return ready, and here's my output, right, which is some chunk of rows, or they'll say, no, I need more input. If you're implementing the poll function directly, poll next, they'll return ready or they'll return pending or whatever if they need more input, I think is what it's called. But then oftentimes we'll implement them as async functions rather than directly implementing poll. And so when you do that, I think the control flow is easier to follow.
Okay. I'm still trying to wrap my mind around the async function versus implementing poll. Do you mind to talk about that for a moment? Because even though I read a lot about it, I'm still like a little bit lost about. Maybe you can help me out with this.
Yeah. So my mental model of what, like, if you do .await in your Rust code, what the Rust compiler will actually do is generate something which returns control, like returns poll ready or poll wait or whatever to the scheduler, right? It'll make some crazy closure, something under the covers, rather than you have to go implement the logic yourself to like implement the poll logic directly yourself. The compiler generates it for you. And depending on what await you call, right, like that will go and effectively call poll on whatever you call await on. If you just made an async function, like the compiler takes care of a lot of the boilerplate for you. Right, so you can call await and it does the right thing. But if you implement the feature yourself, you'll get the call to poll yourself.
My understanding is that it's basically ready the next time it gets called if you just do an async function. Because there's no way that you could say not yet. I mean, you need to actually have a poll function there to say, not ready.
If you write an async function, you wouldn't directly return not ready. But what you might do is you might say, in order to process, I need to read the next thing off a channel or something, right? What you would write is .await. And under the covers, what code would get generated there is it would check, it would basically figure out if you had data in the channel. And if not, the Rust compiler would return poll waiting, poll pending for you, right? So you didn't write any polls, you didn't write returns.
Let's just say you wrote a function that says, meaning of life async, return 42. If I understand correctly, if you'd call meaning of life, .await, it would schedule that to be called later on, and then it would call it, and it would be basically ready and return that value. There would never be a situation where it would ever call it twice. It just says, okay, wait, schedule, run it, it's ready. Okay, that's what I understood. Okay, that makes sense.
Correct. Now, if you wrote a function that has an await inside it, right, the meaning of life, compute earth or whatever, .await, then you get 42. In that case, the future that the compiler would generate might very well return poll pending, right, if the earth future wasn't ready when you tried to await on it.
The inner future, basically.
Yes. This is why I love the async model, right, where you don't need to necessarily understand all the mechanics of how that works in order to write async functions. Right. And so I think it's a huge productivity boost to people to not have to worry about that. Just write your async function, process the batch, whatever, get the next input, and don't worry about the fact that under the cover is all this polling and waiting and blah, blah, blah happening, right? And some scheduler is worried about making sure it's distributed across machines and stuff. I think a lot of people like to complain about Tokio or await or async. It's like the worst of all possible ways of doing scheduling except all the other ones, right? It's not simple, but I've yet to see something that's better. Maybe JavaScript is easier or something, but even when I worked in that, it's probably 10 years ago, so I'm sure it's better now, but it wasn't fundamentally easier to understand. The names maybe were simpler, but the core ideas are still complicated.
Well, I think that most of the things I've heard that negative is well, I have to pull in. I mean, they want us to use this async stuff, but they don't give us a default runtime.
From my perspective, the default runtime is Tokio, right?
Yeah.
I know people don't like to say that, but that's basically what practical reality is.
That's what I basically reply. It's well, pretty much use Tokio unless you have a good reason not to. And there could be, there definitely is reasons not to. I think it's a valid point, but the other thing too is why is this so complicated to do the polling and stuff? It's definitely not straightforward. Nobody who's a CS 101 student could start using async immediately. It takes quite some time.
100% agree. And by the time you put async together with the extension traits that are in stream, right? So if you've ever seen code that's written with async streams by someone who knows what they're doing, it's beautiful. It just looks like this beautiful functional thing, and it's doing all this async stuff, but it's just beautiful. But if you ever actually tried to write that, it's mind blowing getting it to work. There's a huge barrier to entry to figure out how to make all that work together.
Well, that's also one of the general complaints about Rust is yeah, it's kind of simple, but at the same time, once you get past lesson 1.1, then things start getting a little bit weird with all the ownership and everything else. As somebody who's been doing this kind of stuff for a while, when you got to the async part, what was your feelings? Because I think with C, right, you don't really have this kind of async runtime.
I mean, my feeling was I didn't really care about the async runtime, to be honest. I have to have one. Do I care whether it comes from something called Tokio or something called standard? Not really, as long as it works. But no, figuring out was complicated, right? I was going through, I was why are they telling me about poll and what the hell is pin? Why do I have to worry about pin? So I think a lot of times in Rust, you basically need to know what pattern is needed, and that pattern will get you through the first year or whatever, right? Then over time, you get more experience, you understand deeper, and you understand what the pattern is doing, and then you can actually become more general. But I wouldn't try to claim async is easy to understand, or writing those poll functions is easy, or trying to why you have to do pin, or pin still is I kind of understand, but I always fix it by throwing arc all over the place, and that's fine.
Yeah, pinning, my understanding of pinning is data can be moved around in memory, so the location may not contain the data that you needed before. And to me, it's why does that happen? I have no idea.
It's because those await functions are returning control back, right? So your function's returning, right? So somehow you have to make sure that when you come back, the data that you had locally is still there. Anytime I've ever had trouble with pin, easy way to fix it is you either copy the thing or you put it in an arc, and that will solve the problem. but that will impose some small runtime overhead for sure. So pin is a way to actually avoid that runtime overhead by proving it all can't move at compile time, but like, it comes with a major amount of cognitive complexity.
Yeah. So speaking of pin, I mean, obviously with your history, I mean, pin was just something that kind of it takes some time, and I don't know if there's actually anybody. There probably is, but just being a jerk like I am sometimes, it's like, is there anybody who really understands pin?
I certainly don't. I mean, or like not all the nuances, right? I could kind of hand wave, like I could write a architecture level, like one slide with some boxes on it, maybe why it's important, but like I don't actually really understand it.
It's one of those things that people kind of understand, but when it comes to actually explaining it, it's really, really difficult.
In my opinion, it's for some very, very specialized use case, which is like retaining references across function return calls, right? So you basically got to make sure the pointers stay valid across the return, but the return is implicit because it's happening across a wait, and the return is being auto-generated by a compiler. So like if you ever have some problem with pin, it's like the messages that the compiler can give you are just require so much understanding of like what is actually happening, which has been trying to be hidden away from you, but like now all of a sudden you see it in this like 2-page error message that comes out. My personal opinion is that the use cases where it's really important to pin the variable across an await point, maybe in the most high performance web applications, maybe that's important, but the vast majority of cases, it does not matter. But like that you could ever measure any difference in performance.
What I really want to talk about with the pin thing is, how do you feel about the trade situation? Because that's really kind of weird and interesting, and people may like it, people may dislike it. Like I like the derive part when you can actually derive things. Sometimes it's kind of interesting and nice, but at the same time, it's like, how does it derive this kind of stuff? What's your take and what's your feeling on traits? Do you feel it's really interesting and really useful, or
You mean like the auto traits, like pin, send, sync, those ones, or like traits in general?
well, auto traits one, and the other one is just the idea of traits in general, right?
It's kind of like inheritance, right? In other languages, kind of.
Not even inheritance. There's the other one. It's an interface, basically. Sometimes.
Yeah, it's an interface. That's right. That's right. I think it would have reduced the barrier to people adopting Rust if it just had like inheritance, like Java, C++, so people would come and be like, oh, I know what this is. I know this pattern. I can follow it. I think, in my opinion, and now having worked in it for 4 years, there's almost nothing that I've seen that I couldn't do in Rust that I could have done in C++ with inheritance that I couldn't do with traits. Right? Like traits are something they're like you have to express it a little differently, and maybe it would have been more natural to express this thing as a subclass of this other one. But like basically, there's nothing you can't do, in my opinion. So I was talking to some database people, right? The two things they cited why they are not yet ready to move to Rust from C++ was lack of inheritance. Again, I'm not at all convinced that that is critical. And the other one was actually lack of like partial template specialization, which is kind of related to traits maybe, but like, are you familiar with what that means?
I did C++ over 15 years ago. It's been a long time. Just a couple of years in school, and that's about it. So you might need to remind me.
Basically, it's like if you want to provide a trait definition, right, and then you want to have people be able to extend it, but then you want to be able to provide very specific overrides for certain classes. If you look at the Rust standard library, they actually do it. Like they provide special stuff, like special implementations of some of the traits for like VEC and some of the low level containers, because it's important to make sure you don't just use the generic code, but you actually use the specific stuff. The way we handle this in Arrow or in basically lower level is you basically have macros, and the Rust macros situation is definitely better than C++ macros. But you could argue that the macros aren't quite as nice as this partial template specialization. There's some RFC in Rust to standardize them, but I haven't found a hugely difference. Like I wasn't a huge fan of C++ templates in general. So yeah, basically I like the Rust trait system. It's pretty straightforward. It's simple.
If I remember correctly, because at first I did C++. I think it was just C++ for a couple of years and moved on to Java. I remember Java is single inheritance, but I think C is multi-inheritance. Is that right? Or C++?
I think you can do multi-inheritance in C++. My understanding is basically best practices don't do that.
Yeah, that's what I remember. Is like, don't do that because it's unclear what's going on, basically.
Yeah, there's like a bunch of weird corner cases that might be bizarre.
Well, the other thing too I like about Rust is I think sometimes the traits do make some sense because you have like the sync trait, things like that. It makes it a little bit more clear. It's like, okay, well, these things are able to be used across threads, so it's makes sense. Not everything is right.
Yeah, what I really like Rust's the philosophy that if it compiles, it's correct. There's all this like compile time. Yes, it adds cognitive complexity, but basically it's checking a whole bunch of stuff at compile time for you. That if it passes, you get these very nice guarantees at runtime. So like if you get something that says it's send, right? Like you're not going to have some weird ass race condition. or crash or whatever in some weird corner case, right? It's just going to work, even though you might spend 2 hours trying to get the stupid thing to compile. But once it does, you don't spend hours on the back end debugging some weird problem.
So have you actually ran into a seg fault before or no with Rust?
I would say no is the short answer. The longer answer is there was something which is kind of like a seg fault, but it wasn't exactly. It was really a panic in some lower level case. But I think Rust has done a great job in basically living up to the expectation where it doesn't seg fault, right? Yes, it'll panic sometimes, or yes, it'll have overflows or whatever, but actual seg faults, I don't think we've seen any actual memory access violations, which has been not my experience with C++. Very much not my experience.
But starting to kind of wrap up, right? Overall, super happy with the decision. It sounds like you have no regrets, some annoyances, but seems like you're working around them. I mean, is there any other kind of conclusions that you've had since this big write with 3.0 and all different pieces and everything in Rust?
Another thing I wanted to mention was it seems like Rust has been a phenomenal recruiting tool too. I think the people we've been able to hire that wanted to work on Rust have been very, very excellent. So that's been a huge benefit. I also feel like, I don't really know because I don't have enough data, but the open source project didn't work out. I've never really spent a lot of time working on other open source implementations. So I've only really had a lot of Rust. But I feel like the quality of the people that show up and the quality of the code that comes into these open source projects it's very, very good. Far better than I ever would have expected you'd be able to find on the internet. So I said that to a couple of people who I think maybe had different experiences with maybe Python-based projects or whatever, where the quality of the code that got proposed was quite a bit more variable, to put it nicely. And one of the theories was posited, well, because you're in Rust, that basically puts up the barrier to entry, right? But it actually keeps a lot of it makes sure that the people who want to contribute back actually have sort of a sufficient understanding or whatever. So I don't know if sufficient understanding, but I've just been really, really happy with everyone I've met who writes Rust. Everyone seems very happy with it. I'm a believer. I'm a fanboy now. Maybe too much so.
I'm kind of curious about, because you have the borrow checker, everything else. Does that also kind of help to keep some of the garbage out too, right? Because if you're doing C, you could do a lot more damage and things are not so easy to follow up on.
Yeah, there's a lot of really, really subtle bugs that get introduced, right? You got some use after free, or you got some iterator invalidation or something, right? Where it works fine, the test passed, but it's going to seg fault sometime on you in an inconvenient time. So just having the borrow checker, having done that, maybe it's a good point. Maybe that's another level of it prevents certain classes of problems that if you were a really good programmer and understood all the code base in and out, you wouldn't do. But yeah, maybe having Rust do some of that checking for you allows more varied people to contribute. It's an interesting theory.
You did mention something else before too about if you're having issues, just clone, right? Do you get some people doing that kind of stuff when they give you code, or you don't find it so much?
Oh yeah, no, we definitely find early versions of DataFusion cloned all over the place, especially in the optimizer. And we spent actually a bunch of time getting rid of a lot of the clones, right? Being more careful with certain things. Now there's better patterns, right, guys? Follow the patterns and don't involve clones. But at the end of the day, if this code gets in and it clones a couple of things, right, that's an easy fix. So, some subsequent PR, we just get rid of the clones, you make them references or whatever. It's not it's going to crash on you or it cause some huge problem. It's you can make it a little bit more efficient. You can always, code's always improvable. So I don't see it as a huge if it gets cloned a couple extra times and we got cleaned up in some other PR. That seems very reasonable to me.
All right, great. We've been chatting for a while.
Yeah, thank you.
Thank you for all your input. It's good to hear more input from people using Rust, especially those who have gone from other languages that do similar things. Is there anything that we missed that we wanted to go over? Or?
I think I've said probably more than you wanted to hear. I've been a huge fan of Rust. I think, Influx's decision to rewrite the database was very unobvious to me starting, but I was just ready for some coding job. I wasn't worried about the larger term strategic implications at that point, but I feel like we've been able to really build some really cool new technology, and I'm very excited as it is able to get rolled out to more and more people, that hopefully other people can see the value of what we built using Rust and all these other cool technologies.
Okay. Well, it's great having you on. I really appreciate hearing your experience with it. Happy to hear that you enjoy it. I'm also happy to hear what you don't like about it, because I always think that we need to hear more about, what works, what doesn't work, because there's no silver bullet, right? But I'm glad to hear that it seems like 95 to 99% of what you're running into is overall positives.
Yeah, well, you always got to think about what's the alternative? I can go write in Python and not have any async problems, right? But it comes with its own other set of trade-offs. Everything in engineering, there's a set of trade-offs, and I think for writing databases, the set of Rust trade-offs is pretty good.
I definitely agree. It's a great language. And the fact that so many companies are pumping big investments into it definitely shows something too.
Yeah, we'll see. Maybe it'll have been a fad, right? In 5 years, we'll talk about some of the language, but I think it's got longer staying power than that.
Yeah, I think you're going to find a lot more Rust stuff, especially with what other kind of exploits is going on.
Oh yeah.
Great having you on. It was great to hear how you guys are doing with Influx and your Rust writing, and it's going great. Thanks again for coming on, and hopefully I'll have you guys back again, maybe when 3.0 comes out or 4.0, who knows? Maybe there's something more interesting down the pipeline.
Thank you so much for having me. It's been great.